Hello, welcome to Mathematics for Machine Learning. Today we will discuss the fundamental theorem of linear algebra. We will take a big picture view on linear algebra and in particular on linear maps that go from Rn to Rm. These linear maps, as we know, are given by matrices, in this case an M by N matrix. So let's start out by looking at this linear map from X to AX, which goes from Rn to Rm. We know that using the singular value decomposition of A, we can perform this linear map in multiple steps. First, performing a linear map only with the right singular vectors, then a linear map using this diagonal matrix holding the singular values, and then a linear map using the left singular vectors. So if we look at what happens to this set of vectors if we multiply it by A, so if we perform this linear transform, in this example we're going from Rn, where n equals 2, to Rm, where m also equals 2. Now if we do this multiplication by A, this linear transforms in steps, first multiplying with V transpose. Remember, these are the right singular vectors, and they are an orthonormal basis of Rn. Which means that if we multiply with it, we only perform a rotation. So the original standard basis, this is E1 and this is E2, are being rotated. So they're not aligned to the coordinate axis anymore. The next step is multiplication of the resulting vector by sigma. Sigma is a diagonal matrix holding the singular values. Remember, the singular values are ordered by their magnitude and they are all larger or equal to 0, where the first r, starting from the top left, are larger than 0 and the remaining ones are exactly equal to 0. That means that the first r dimensions are being scaled. So if this was a 1, we're now scaling to sigma 1. And similarly along this direction, if this was a 1, we're scaling to sigma 2. Accordingly, these original E1 and E2 are now scaled because they are a combination of these two vectors here. The third transformation is another rotation by the left singular vectors. Again, the left singular vectors are an orthogonal matrix, which means that we perform a rotation, but all the lengths stay the same. So we see that these original vectors that originally were axis aligned are now both changed in their length, but also in their direction. Now that we have set the stage and know what we're talking about, so we're using a matrix A to do a linear transform from Rn to Rm, we can discuss now the fundamental theorem of linear algebra. So if the matrix A is such an M by N matrix that forms this linear transform from Rn to Rm, then we can state certain things. Remember that A transpose, in this case, is an N by M matrix, meaning that also A transpose is a linear transform that goes from Rm to Rn. Now we can discuss about certain properties of these spaces. we see here in this picture the 4 fundamental subspaces of A. On the left side, we are in Rn, and on the right side, we are in Rm. And if we take a point from Rn and multiply it by A, we are mapping it to some point in the range of A. So the range of A is the set of points that are reachable by multiplying x with A. Now, if x is in the null space of A, that means that it will be mapped to the 0. Note that the 0 is also, of course, element of the range, because the range is a subspace. So the 0 element needs to be included. Similarly, if we multiply some point x prime with A transpose, it will be mapped to the range of A transpose. Note that it is not possible to reach a point that is outside the range of A transpose. So this cannot happen. Let's go back to the theorem now that we have set the stage. So the first part of this theorem says that the null space of A is orthogonal, or the orthogonal complement for range of A transpose. So it says that this subspace here, the range of A, is orthogonal to the null space of A transpose. So we will prove this part of the theorem a little bit later. For now, let's just assume that it holds. So we assume that the null space of A is the orthogonal complement to the range of A transpose, because this will help us actually prove the remaining parts of this theorem very quickly. The second part says that the null space of A, so the set of vectors that if we multiply it, map exactly to 0. If we perform the Cartesian product of this null space with the range of A transpose, this part here, we get all of Rn back. Now note that we have agreed on that the first part, for now, we can believe in to be true. So assuming that 1 is true, then this part is pretty clear, because both the null of A and the range of A transpose are subspaces of Rn. And the range of A transpose is the orthogonal complement to the null of A. And we know that if we take one subspace and perform the Cartesian product with the orthogonal complement of this subspace, then we get the whole vector space back. So this is Rn. Third, the dimensionality of the range of A plus the dimensionality of the null space of A is n. This is also separately known as the rank nullity theorem. So what have we said? The dimensionality of the range of A, namely of this part here, plus the dimensionality of the null space of A equals n. Now, this is a little bit funny because the range of A, of course, is a subspace of Rm, not of Rn. So we get there by taking a vector and multiplying it to there. But we know that the dimensionality of the range of A is given by the rank of A, because A can only map to something that can be spanned by the columns of A. And the rank gives us exactly the number of these linearly independent dimensions. So all above the rank are dependent. Now the same is true for the row space, so the range of A transpose, because the rank of A and the rank of A transpose are the same. And because we know that the row space and the null space, so the range of A transpose and the null space of A, are orthogonal complements of each other, and their Cartesian product forms Rn, it follows that, well, the sum of their dimensionality needs to be exactly equal to the dimensionality of their Cartesian product. So this is rank of A, which is R. This here is n minus R, because together they are Rn, meaning that their dimensionality equals n. Fourth, if we have the singular value decomposition U sigma V transpose of A, then the columns of U and V form the fundamental subspaces of A. First, the range of A transpose, so the part of Rn that can be reached by taking a vector from Rm and multiply with A transpose. Is spanned by the columns of V. In particular, only the first R of them. 1 through V R. Remember, only the first R singular values are actually larger than 0, meaning that the remaining n minus R, which form the null space of A, will never be used. So it's impossible to map anything to the null space. So these are V R plus 1 through V n. The range of A is spanned by the first R columns of U. U1 through U R. And finally, the null space of A transpose is spanned by the last M minus R columns of U. So UR plus 1 through UM. Now let's look at what happens if we take, for example, V1 and multiply it by A. So we're interested in A V1. Now remember that A is diagonalized if we multiply it by V from the right and U from the left. So A equals U sigma V transpose. It follows that now if we take the whole thing and right multiply it by V, then this V cancels here and we are left with U sigma. So if we're only looking at V1, the first column of V, V equals V1 through Vn, then we see that V1, if we multiply it by A, becomes sigma 1 times U1. So this, assuming that sigma 1 is larger than 1, it would be mapped to this point here, sigma 1 U1. Similarly, if we take VR and map it by A, we get this point here. Remember that VR is the dimension corresponding to the smallest sigma that is larger than 0. So this will have a magnitude that is smaller or equal to the one of sigma 1 U1. Sigma R U r. Now if we take any of these here, then they will become sigma r plus 1 times u r plus 1, but we know that sigma r plus 1 is 0. So all of these will map to 0. And any linear combination of them also will map to 0, which means that they span the null space. Now let's look at what happens if we take this point here and map it over here. Now of course this will go somewhere in the range of A. What happens if we take this point here and map it? Well, it's being mapped to 0. It follows that if we take their sum, that this will also go to this point. So we're taking the sum of a point x and x prime and taking ax plus ax prime. We know that ax prime is 0 because x prime is an element of the null space of A. Thus, this part of the sum will be mapped to 0, and the remaining part of the sum will be x or ax. So this will go to ax. Now hold on just for another minute, because remember we agreed on to just assume that the first part of our theorem is true. Just to ensure that our whole building doesn't collapse, let's quickly prove it. Remember the first part said that the null space of A is the orthogonal complement to the range of A transpose. Let's start with the proof. So X element null of A means exactly the same as, well, that ax equals 0. Now, if we look at this sum and rewrite it using the rows of A, then this is equivalent to saying that, well, every element of this null vector being 0 means that for every row AI transpose X, we get a scalar 0 back. So the inner product between this row and X needs to be 0 for all I in 1 through M. Now if this holds for any row, it of course also means that it would hold for the sum of all of these rows. So I equals 1 through M AI transpose X equals a scalar 0. Actually, it still has to hold if we multiply these with some scalar alpha for all alpha I. Now if we take this sum and pull out X, we get the following. We get a vector that is the sum of all our alpha I, these scalars, times the ith row of A. Take the transpose of that, multiply it by x, well, it still has to be 0. This sum, if we plug in arbitrary alphas, represents the set of all possible linear combinations of the rows of A. Thus, it's basically any member of the row space of A, if it holds for any scalar values alpha. If we call such a vector V, that means that this is equivalent to saying that if we take such a V from the row space of A, and remember the row space of A is the range of A transpose, then V transpose X equals 0 for all X element range of A transpose. What we have proved so far is that any combination of the rows of A, so any element in the range of A transpose or the row space of A, is orthogonal to any X in the null space of A. So it means that X being an element of the null space of A is equivalent to saying that X is an element of the orthogonal component of range of A. And this is exactly what we set out to prove. And with this we have proven that one holds and all the other things are fine. So, and this allows us now to say goodbye to the day after this lecture on the fundamental theorem of linear algebra. Bye bye.